Okay, continuing with acids and bases, we're going to talk about the acid-base dissociation constant. And really what we're talking about for an acid, that would be a Ka. For a base, it would be Kb. If we have a weak acid, we're going to represent that acid as just Ha, with that A being some kind of anion. It doesn't fully dissociate or ionize, so it sets up an equilibrium with the hydronium ion in solution and that anion in solution. As with any equilibrium, water being a pure substance doesn't go into the expression, so the equilibrium constant would be the hydronium times the anion times the acid in its molecular form, which would be the reactant. And this is known as your acid dissociation constant. There are several types of calculations that can occur with a weak acid. Say, for instance, we have the Ka for acetic acid given as 1.8 times 10 to the negative 5. And the question asks for a pH. Calculate the pH of a 0.10 mole per decimeter cubed solution. All right, the first thing you should do is start with the equation for the acid and show its ionization. I'm going to drop state symbols, knowing that these things are in aqueous solution with the exception of water being that pure substance. And what you're going to do, if you remember, we set up an ice table. Initially, you assume that all of the acid is in its molecular form. I usually draw an extra amount myself, but water is not going to enter into this equation. And initially, you're going to assume that there is no ionization. Hopefully, from the Chatelier's principle, you can see that the equilibrium is going to shift to the product side. So we're going to lose some kind of concentration here, and we're going to gain it here. Remember, in an ice table, it is only concentration. Okay, so at equilibrium, we will have 0.1 minus x, and x, and these should have been plus x, because it's shifting that way. Okay, because our Ka is 10 to the negative 5, we're going to assume that this is small compared to the 0.1. So we're going to say at equilibrium, the concentration of the molecular acid is 0.1. Right. Your Ka is your concentration of the hydronium times your acetate over your, I'm drawing it weird, sorry. That is 1.8 times 10 to the negative 5th is going to be equal to x squared over 0.1. Solving for x, you get 1.34 times 10 to the negative 3rd. That is less than 5% of the 0.1, so your assumption here was good. So I always kind of write like 5%, okay. Then you can, and by the way, this, I'm running out of room on my little slide. You really do 1.34 times 10 to the negative 3rd over 0.1 times 100%. That has to be less than 5. Okay. So this x is the concentration of the hydronium. So then you can find the pH by taking the negative log of that, and you should get a 2.87. Most often, you're going to be able to make this assumption. Most often for IB, this assumption here is going to be valid. Okay. Okay, kind of a random fact. There's Ostwald's Resolution Law. And this just states that as a solution becomes more dilute, a weak electrolyte will become more dissociated. Okay. All right. Okay, a subject that there are more examples of acid-base equilibrium calculations. I think your work packet, the review packet, kind of covers them very well, so make sure that you look at all of those. All right, now let's look at something that can be confusing. If we look at salt hydrolysis. Okay. Salts are ionic compounds. And if they're soluble, they do completely dissociate. Okay. So, for example, if you have sodium chloride, put it in water, I get sodium ions and chloride ions. This is going to form a neutral solution. Okay, now, salt hydrolysis is really determining when you have an ionic compound in water, what are those ions going to do? Well, theoretically, so in theory, your sodium is going to attract the hydroxide part of water and theoretically go to make sodium hydroxide. But you know sodium hydroxide is a strong base, so it will not be in equilibrium, and it would go to that way. So that does not contribute to any pH change. Same thing with the chlorine. It is going to be attracted to the H, or the hydronium ion. That is a strong acid. We know that strong acids do not set up an equilibrium, so we know that the chloride's not going to have any effect on the pH, so it would be a neutral solution. Now, what if we have something like sodium acetate? Well, sodium acetate is going to form the sodium ion and the acetate ion. We already know that the sodium ion is going to have no effect, but what about this acetate ion? It's a negative, so it's going to attract the hydronium ion, and it's going to form CH3COOH, and I have to make this water, I'm sorry, and hydroxide. That is a weak acid, so this will set up the equilibrium. All right, so this ion will have the effect of making a basic solution. Taking a look at another one, NH4Cl goes to make the ammonium ion in solution and the chloride ion. We already know the chloride's not going to do anything, but what about this NH4+? When I put it in water, it's going to form NH3 plus the hydronium ion. That is a weak base. This will set up an equilibrium. This will form an acidic solution. Looking at the acidity of salts also depends on the charge and the size of the anion. Of the cation. Okay. So, for instance, if we take a look at aluminum chloride, when I put this in water, if you remember from the periodicity chart, it's going to form aluminum, hydroxide, and hydrochloric acid. Okay. Now, The aluminum ion, Al plus 3, is small and highly charged, high charge density. And you may or may not remember that this aluminum is really going to form the complex ion, this. And that complex ion is going to set up an equilibrium where it dissociates and it actually sets up successive ones with more hydroniums being liberated into solution. All right, but this is the complex ion. Okay, you would see similar reactions with iron plus 3 and to a smaller extent magnesium. All right. We're going to talk about buffer solutions and look at some graphs in the next screencast.